Okay, hi everybody. We're doing a wee demo this morning to determine the internal resistance of a cell. This is a remake of a video I made about 9 years ago. So hopefully it'll be a wee bit clearer and hopefully we'll get the same result. So we have a 6-volt battery pack there, 4 1.5 volt cells, but we're only using 3 of them. And our TPD, our terminal potential difference, these batteries must be brand new. So we're getting 4.55 volts across the terminals of those 3 cells. And I'm going to put that in my table here. So here's what we're doing. We're trying to determine the internal resistance of a single cell. We're going to measure the terminal potential difference across the battery with no current flowing. So we've got 3 bulbs here that are in parallel and none of them are connected just now. So I've got an ammeter there that's measuring 0, and therefore my TPD when no current flows is equal to the EMF, and it's 4.55 volts. So I'm going to put that in my table here. And then we're going to add the lamps in parallel one at a time and measure the current and the TPD for 1, 2 and 3 lamps. And then plot a graph of the TPD against the current, and from that graph we are going to determine the maximum current we can get from that battery pack and the internal resistance of the battery pack and then the internal resistance of a single cell. So let's get going. So got my 4.55 volts in, that's the TPD when no current flows, and then I'm going to connect a single bulb on its own and that bulb will light up. We will get a current on the ammeter. I'm using the 1 amp shunt, so I use the top scale, which means it's got a full scale deflection of 1 amp. So at the moment it's reading about 0.3 amps top scale. So 0.3 amps, and my TPD has fallen to 4.2 volts. So let's put them in the table. I've got 4.2 volts and 0.3 amps. Then I'm going to add another bulb in parallel. So put that in. Now we've got our 2 bulbs, and my current has gone up to 0.4. Let me think, 0.42, 44, 46, 0.47 amps. And my TPD is 4 volts. So TPD is 4 volts, and that was 0.47. Let's keep going. I'm going to add another bulb in parallel. This time my current has gone up to, remember my full scale is 1 amp, so that's 0.62. Yeah, 0.62. 0.62 amps and 3.82 volts. So 3.82 and 0.62. That's our results. I'm going to have a little look at them on a graph. And as I say, from the graph, we will get the maximum current available from the cells and the internal resistance of a single cell. See you in a mo. Right, if you want to have a go at drawing a graph of these results, there is my results table. So if you're doing that, put your current on the x-axis, put your TPD on the y-axis. Now you might notice from the table here that as the current increases, the TPD decreases. So you're going to get a graph with a negative gradient on it. It's going to start at 4.55 on your y-axis, and it's going to decrease. Now, that y-intercept, where your graph cuts the y-axis, the y-intercept is the maximum voltage. That will be equal to the EMF of the battery pack. That's the voltage, that's the TPD when no current flows. The gradient of your graph, because your y-axis is voltage and your x-axis is current, then the gradient will be V over I, which is R. It will be equal to the internal resistance of the battery pack. And from that value, you should be able to determine the internal resistance of one of the cells. Your x-intercept, if you extend your graph so that the line cuts the x-axis will be the maximum current available from the battery. Right, there's my graph. As you can see, it's a negative gradient. I've asked Excel to show the equation of the line on the graph. So there, it's in the form of y equals mx plus c. So my y-intercept is 4.55. That's the maximum voltage, which is equal to the EMF of the cell. The gradient of the line is a negative gradient. It's 1.2. So that's the internal resistance of the battery pack that we used, 1.2 ohms. Remember, we used 3 cells. So that means the internal resistance of one of the cells must have been 0.4 ohms, 0.4 ohms. And the maximum current we could get from this battery pack, well, I extended my current axis up to 4.5 amps. And you can see that the line cuts the x-axis at about 3.8 amps. Now, you could have found that as well by substituting 0 in for y on the equation of the line. You would get 3.8 if you did that as well. But that's the maximum short circuit current from the battery. You couldn't get a current of any more than that from that battery because of its internal resistance. If you work out I equals V over R and do 4.55 over 1.2, you'll get 3.8 amps. And it's because of the internal resistance that there is a limit to how much current you can get from batteries. So remember, we got a total internal resistance of the 3 cells of 1.2 ohms. That means that one of the cells has an internal resistance of 0.4 ohms. And I looked up the manufacturer's data sheet, and it told me that the internal resistance can vary between 0.1 and 0.5 ohms, depends how fresh the cell is and what the temperature is. But that's an investigation for another day. See you in the next one.